Yeah,
Okay.
thanks for remembering me.
Oh, no problem. I
Yeah.
just wanted to, because I'm pretty much sure this is like early morning and probably not everyone would be here, and or it's just different
Yes.
time zones. So I just insist on doing recordings because then somewhere on the other hand, people can actually look at it in their off times or when
True.
they're available.
Yeah. Perfectly fine.
Okay, thank you, Dr. Jain, and thank you, Pooja, for the kind introduction. And today's tutorial, we will be talking about knowledge-infused reinforcement learning. And essentially, this is a line of work that we are pursuing at the Artificial Intelligence Institute. And this is very much in line with the tradition of using knowledge graphs and semantic web in understanding the behaviors of artificial intelligence algorithms, and essentially more importantly, from the perspective of that these algorithms as they stands are statistical black box. When I say black box is you get the results, but it's a lot about depending on your interpretability, your perspective. You want to nudge the whether the outcome is relevant or not. And essentially you look for various online resources or databases to match your outcomes. So here in the tutorial we will be talking about a series of strategies, methods, as well as evaluation metrics that will delve into the details of how things like user level explainability and interpretability can be achieved using the knowledge structures, and specifically in the context of reinforcement learning, because that's a very much close machine learning framework that involves human and AI teaming. So uh, yeah. So a brief about the tutors. I'm Manas Gaur. I'm a researcher at the AI Institute, and I'm also a senior AI researcher at the Samsung Research America. My research is broadly classified into knowledge-infused learning, which is the new paradigm that I will be introducing today, natural language understanding and knowledge graphs. The other tutor is Kaushik Roy. He's a PhD student at the Computer Science Department, as also a researcher at the Institute. His research is along the line of knowledge-infused learning in reinforcement learning systems, as well as in conversational systems. So let's just start from the very understanding that these are this class of algorithms that I will be talking about, or this tutorial will be discussing, is applied around various domains. So it can start with a conversational AI domain where the task is to contextualize and personalize the conversations. So when I say contextualize means that when you are talking about a particular topic, the model can able to understand what context you're coming from. And when I say personalized means over the time the model develops a sense of a small, or you can say a small database at the back end that talks about your context, so you can have so the model can have a personalized conversations with you. Another use case for knowledge-infused reinforcement learning type frameworks have been in matching support seekers and support providers in dynamical systems. For instance, the crisis response in the pandemics. Another utility has been in the education domain, where you use reinforcement learning in developing Rubik cube solvers that can also help. If you deploy it into a conversational framework, it can be used to explain or educate children how to solve a Rubik's cube. Another interesting direction for knowledge infused reinforcement learning has been in the direction of food, where you want to develop a framework that is allergy aware, and that understands that which are the allergies are associated with some recipes, and given a preferences or user preferences on allergies, you can define you can personally define a recipe so that the user can have that, or that recommendation is associated with the user preferences, where the preferences are allergy associated. In this today's tutorial, along these various domains, we will be specifically focusing on the conversational AI, but essentially whatever we are talking about today are applicable to all of those domains as well. So let's just start from the very basic. of how do we build a conversational system, or how do we build a conversational agent. So essentially what you do is you take off the shelf state of the art natural language understanding models, which as of now are the transformer models, and you provide them a series of data sets which are large amount of textual data, and you do weeks of training on this on such data sets, and you at the end you generate you get a trained generative model. This generative model, if you can utilize, you can put it into a conversational system, and you can interact. It can help you conduct an interaction between the user and the agent. So in this setting is pretty much applicable in a general domain where the conversations are about food. It can be conversation about travel planning. Conversations can be about a domain like sports and so on and so forth. But things become a little bit complicated or diverse when you are dealing with a conversational system in the context of mental health conditions. If I use this trained systems, even in spite of the large conversational context or the passages from where this model is being trained from, if you put it onto the mental health condition, there are slight issues that have severe consequences as well. For instance, in this case, if a model is asking, do you feel nervous, and you reply more than half the days, then these are the series of questions that are being generated by the model as a follow-up. And if you look at these questions carefully, these questions are not the questions that a clinician would ask. Though we know that the last question in this is sort of acceptable, but the remaining one is not. And the selecting which one is best is still probabilistic. So you will do a kind of a sampling approach to pick which of the questions is suitable. And at the end, it is a high chance that even the first two questions are picked, and then they might have some negative connotations associated with it. So uh, in this unsafe question generation processes, you are okay. Okay, sorry. So these unsafe questions are certainly not the ones that your model should be generating. So how do we deal with this strategy? So essentially, what we do is uh, I just go over the literature review quickly. So there are certain issues that this models have been tested. So there have been several models that we have tested so far that have resulted in some factually incorrect responses, questions that are like aren't safe. For example, BlenderBot 1 and BlenderBot 2 are certainly those systems that have not been able to generate factually correct responses in the context of mental health. OpenAI and DeepMind's Retro and GPT-3 aren't safe because they have been trained on the huge internet corpus, and that do not, even if you do fine tuning and localized or even you use frozen embeddings of these models, still the generated questions are not safe until unless that comes in like Google's Lambda model, where they utilize Google's long list of safety guidelines to place constraints on the safety. So that means that in order to make your bot safe, you need to use some kind of guidelines, some kind of a process structure. And that's kind of something that we want to exercise, and that's where we want to move forward in the conversational systems. So keeping the same context that the model is still in the wild and it is generating factually incorrect questions that can be risky. Essentially, how do we solve it? So we introduce a very intuitive method called safety checks. So what essentially safety checks are? So safety checks are nothing but a set of rules. The rules are that if the current question, the generated questions that the model has generated, if you tokenize that sentence and find their intersections with some safety lexicons, you get some probability values associated with the outcome that you're getting. So you match your generated outcome to some safety lexicons. Simultaneously, you also calculate a similarity, or kind of, let's say, every question is nothing but a sentence. You can do sentence embeddings and compute similarities between the generated questions and the questions that are there in the medical questionnaires. So you kind of reach into a ballpark of whether the generated question has some degree of safety associated with it. And if you have, if some questions are very strongly related to these questionnaires, you kind of copy the questions from the questionnaire and just remove or subsume the generated questions. So in this scenario, if we're using the safety checks, the generated questions are medically valid because you're having a medically validity. And since medically generated questions are already safe, so you attain a certain level of safety associated with it. In this process, there is a significant improvement. When we tested it on a larger data sets on mental health care, which we have built over the time, we found that if you do not use model, do not use process, not like this kind of like safety constraints, your model is prone to generate more than 15% of your unsafe questions. And on the other hand, if you use safety constraint, this thing goes significantly down. So if you just look at the comparison between an attention model and another attention model with knowledge infusion in it, when I say knowledge infusion, it's some sort of like constraints. It can be of any form. Like I'm just not only focusing on knowledge graphs as of now. So the reduction is significant in just with just introduction of just simply simple safety checks. So how does this thing looks like? What's actually happening under the ground of how when we are mapping these informations? So essentially, what happens is that this is on the left is you see an attention model. You are the system is the person asks a question. I feel bothered by little interest and have a little least pleasure in doing anything. And these are the questions that the model has generated. If you look at these questions, did you check your dopamine levels? Do you feel your brain is affected? These questions are like, you see that these questions are something people ask on the web blindly, and these are the questions that a clinician, a well-educated person who is actually treating a patient would not be asking these questions. So when we look at the similarity between these questions to these lexicons, so first lexicon that we have we use is the DSM-5. So when I say, like, to all the people over here, DSM-5 is a diagnostic statistical manual for mental health. It's a kind of a knowledge resource for various mental health disorders. And essentially what you're trying to do is you're computing the similarities between line by line by in sequence with these questionnaires to figure out to what degree of similarity does these questions have. So you essentially see that these questions have a very little or minuscule similarities with these lexicons. On the other hand, if you have these questions that are very much oriented by the safety checks, right? So these questions have a high similarity with these lexicons. So you over here, not only you check that your outcomes are better, but you also see that the outcomes are now very much safe in their like visual sense. If you do a visual inspections, the generated questions are much safer than just generated in the wild. So you did two things. You introduce a safety checks, and then at the end, when the outcome generated is there, your question is being generated, you match those questions to these lexicons. So under the hood, what we did was in this safety checks as a very interesting process. So this process is something that a clinician or any human being would actually follow. So we say that so generated question can belong to one of these categories: cause, symptoms, medication, and treatment. So if we say if the previous question was about the cause, then the current question should be about the symptoms. If the previous question is about the symptoms, then the current question needs to be about the medication, and so on and so forth. So if you see, this is a particular process that you're bringing in, and this goes back to the very old symbolic AI strategies that were out there in 1960s and 1970s, where things becomes really meaningful because you are governing what is going inside your model, making your model more interpretable. And explainable is definitely there because this is what your model will yield as an outcome, and you can match it to the resource that was being used to generate these rules in the first place. So you are actually having a codependency between model interpretability and user level explainability. So in this process, when we looked at this thing that, okay, we did a safety checks, we got improvement, we achieve user level explainability, we have interpretable systems now, but still this is just one task. This is just one application where we are dealing with what's happening under the hood, why such a systems are not actually explainable or interpretable. And so the major issues lies in the fact that these models are developed on labeled data sets, and these labeled data sets are not just one shot processes. They are constructed by human annotations, and human annotations are not just straightforward approaches. They comprise of experience, they comprise of web search corpus, and they also comprise of expert guidelines which are being constructed to achieve a gold standard data sets. But essentially what happens is that these resources, though are available, are being used in creating the data sets, but they're not available to the models, neither into the model to control its representation learning framework, neither they are being given an output to match that whether the outcome is correct or not according to the user level and users understandability. So that forms a major crisis on why there is an issue between an input and an output, and you have to deal a lot about you have to deal a lot in the uncertainty and risk. So one process would be, why not just, we are all aware of knowledge graphs. We know knowledge graphs are like subject, predicate, and object triples being connected with each other. And you can have various forms of knowledge like lexicons and knowledge graphs and ontologies. They, in a very simple sense, we call it like an information graph, because they contain some information. You put them, you use them, you can use them by querying them, and you can use them into your model. But here the issue lies that these knowledge graphs are very heavy. There are millions of nodes, and you cannot use them straight away as it is into your model. So there are some workarounds, and that's what we will discuss today. And in the remaining part of the tutorials also, we'll use this notion that how do you do infusion of these knowledge structures in a more efficient way. So let's just introduce some quick two terms that I've been talking about very recently. That interpretability is defined as a process where we use this kind of a knowledge structures into your model. That's what we termed as a model interpretability. And the second thing is the user level explainability, means when I have an outcome from the model, I could match the outcome to these knowledge structures. And when I say mapping, it can utilize any metric systems. To my personal best, I understood bipartite matching to be the most suitable way of assessing the user level explainability. So this knowledge structures, the information graph, can be seen from these three different ways. You can actually have a process knowledge, which is a structure, a kind of a flow chart of how the questions needs to be asked, and that can be a kind of a flow. Or you can use concept net, which is a lightweight and easy to integrable way, though you can use it either as an API or you can use as a word embedding methods. Either way, the things are really flexible in ConceptNet. Or you can use healthcare lexicon specifically for the particular domain. So healthcare, if I are talking about, we can use DSM-5 as a lexicon. If you are using any other domain, you can have other domains as well. For instance, let's say in US, we have the crisis issues. And for that, the FEMA, the Federal Emergency Management Agency, has constructed an archives. So you can download those archives, and you can construct a knowledge repository from those archives, and you can use it. It's very similar to how you use a medical information in UMLS, which is a unified medical language system. So these are the different variants of lexicons. So we all know that there are various forms of knowledge, that's why we call it information graphs. Some of the knowledge graphs are constructed through manual efforts like ontologies. Some of them are constructed automatically. For that, what I was talking about, using PDFs and some archives. So if you see at the very lower end, the D is an education knowledge graph, and it is being constructed by a company called Imbibe in India, which works with Reliance Jio for educations. So they have a very fascinating way of constructing a new form of knowledge graphs, which you not only construct and you do not have only entities and relationships, but you also have constraints. And then there are other set of knowledge graph that you constructed automatically, that your model constructs by using embeddings approaches, by noun phrase extractions. You do constituency parsing, or you do some parsing methods, and you figure out noun phrases, verb phrases, and you kind of associated them and construct a knowledge graph. So there are various ways of constructing with the knowledge graphs. So a very intuitive distinction that I'm aware of between ontologies and knowledge graphs are, like, ontologies, you have a curated and they have a schema, and there is no standard schema for knowledge graphs. So here what we today's talk in remaining sections would be talking about a very particular form of a knowledge, which is what we call as a process knowledge. And it is at the intersection of a knowledge graph, and it's also a kind of an ontology as well. Here the schema is defined based on the information being present in some resource, some kind of an expert resource, that all the clinicians and all the doctors, or maybe emergency response or emergency providers, weather forecasters, and all those people actually uses. So for instance, in this case, what you can see over here is a clinical questionnaire, which is called Columbia Suicide Severity Rating Scale. And this scale is being used to assess the suicide risk of an individual. And if you see this questionnaire carefully, there are some questions associated with it, and every question has some kind of a description. So what we are trying to do is we are modeling these set of questions, which has yes and no at every point, into this kind of a flowchart on your right. And this flowchart is nothing but a process knowledge. We make the model follow this process. We say that if the question 1 is answered, then only ask the question number 2. If the question 1 is not answered, probably 2, 3, 4, and 5, and 6 are not the question that you should be asking. So it governs the model in a very much directional sense. Another form of so this is a structure of a flowchart, and this can be another form of process knowledge, which is more like flattened. Here there is it's more like if you can say, it's more like a tree, n-ary tree. So here you have a root node which measures the general anxiety, and all the leaf nodes are the different questions that defines this anxiety assessment. And what you do is that you say that there is alpha and there is 1 minus alpha. So alpha means whether the question is being answered, and 1 minus alpha, the probability when the question is not being answered. So you have both of this information. And if you look at this alpha and 1 minus alpha, a very intuitive method that can solve this approach, that what Kaushik will be talking about next, subsequently, would be the decision tree. So probably we go back into the very old machine learning methods of which are very much interpretable, and utilize how knowledge can help model some decision tree structures that we can use them to solve some of the challenging problems in mental health. So with this broad understandings and motivations that I have provided to you, let me just give you a concrete definition of what we mean by knowledge infusion at large. So this is knowledge infused learning is a class of neurosymbolic methods that we have built that are majorly focused towards incorporating broader forms of knowledge, like lexical, domain specific, common sense, or constraint based, and they are basically used to enrich the model's capability to be more interpretable, transparent, and can be able to provide some user level explanations. So essentially, at a very high level, it is the a dual play between the data and the knowledge. And essentially, that's how a human makes his or her decisions. So let's start with the first form of knowledge infusion, which is a shallow infusion of knowledge. And today, in the remaining part of the talk, we will be only focusing on process knowledge, which is a new form of, I would say, a sequential knowledge, as knowledge graphs and ontologies are not non-sequential. You can make them sequential, but as they stand right now are non-sequential. So this is more like a sequential structure of knowledge. So how do we define shallow infusion? So shallow infusion is a method, or we say strategies are being classified. The AI strategies that are classified as shallow infusion includes word embeddings, graph embeddings, and all those structures which kind of encodes your information. So essentially, the idea of shallow infusion is that you have a user post, and you know that which of the posts or phrases within your post can answer which of the questions. Your task is that how can a model identify these pieces of information correctly so that it can answer these questions in the PHQ-9. So PHQ-9 is a depression questionnaire, just like anxiety has a questionnaire, and suicide has a questionnaire. Depression also has a questionnaire. So this is a 9 question questionnaire. So the task of shallow infusion is to utilize this input post and generate some embeddings, and essentially you want to learn a kind of a loss function that would take the representation of this input post and match it with individual questions in this PHQ-9. So you get a probability vector of length 9, defining the probability of whether this post answers to which of these questions. So above a particular threshold, you will mark this question as yes, and if they are not above the threshold, you mark them no. A very interesting utility of this such an approach is now you have a series of yes questions and series of no questions, and those no questions are the questions that your model would be considering as a potential follow-up questions to be asked to the user. So now your question is, your model is not generating questions in the blind, but rather there is a strategy behind of why this particular questions are being generated. And this makes us this model user level explainable and safe, because now you can actually match why this particular question being answered by mapping the particular questions to the phrases that constitute to the yes and no. And also you can it's safe because now we are using clinical guidelines which are approved. So if a clinician says we want to enrich PHQ-9, the system is pretty much flexible, because now rather than having, if there is a PHQ-10, that means there are 10 questions. Now you have a 10 probability 10 length probability vector to be for your loss functions, and you can match your inputs to those questions, and see whether your questions are actually being answered or is just being a random situation. Another form of infusion is a semi-deep infusion, where we try to nudge, or I would say not nudge, I would say you try to infuse or make your model in a way that you use the model is now have an interpretable structure. So a very simple methods for interpretability are decision trees, naive Bayes, and k nearest neighbors. And knowledge, so the task would be that we take any of the shelf language models that can encode a large input text, and on the top of it we introduce a kind of a decision tree structure. So our framework remains the same as in the shallow infusion, but what we top up with it is an interpretable ML model. In this case, is a decision tree. So now decision tree forms this particular hierarchy that these questions have been answered and this question has not been answered, and you use a kind of a Bernoulli loss function between the generated questions, between the questions that have been answered and the questions that have been answered yes and no in the so essentially what you will have now is not a probability vector, but rather a tree that will that every node of the tree would be a question. So you will have a tree now that looks like, okay, this question has been answered, this question has not been answered, and so on and so forth. And you match your tree with the ground truth tree, and you figure out that whether these matching are similar now. So now you will have a structural similarity between the two end. And this process is pretty much same. It's user level explainable and safe, and an interpretability that is being introduced with semi-deep infusion is because of the decision tree, because decision tree are the interpretable class of machine learning algorithms. Another form of which is the final and the most important form of infusion is the deep infusion structure, where the task is that we are not only stacking up the knowledge at the only at the one point of your classification structure, but rather we want the knowledge to be model as a when a language model is learning. So if you look at this structure here, we use pre-trained deep language models for representations, and in deep infusion where we are trying to develop a new set of deep language models that are, when they are learning, they are matching their learned representation, their latent representations with some of the information that are there in the questionnaires. So there is a knowledge control. So in this process of deep infusion, there is so what essentially we are trying to do over here is that the knowledge at every layer, there is a testing. There is a test whether the generated representation at particular layer matches to which a set of questions your process knowledge. So essentially you're trying to say that your process knowledge now would not be the same. Now I cannot have PHQ-9 be tested in this layer, because if that happens, then I'm biasing my model. So what we did was we replaced PHQ-9 with a larger set of questions. So SCID is a structure you're trying to map these set of so every learned checking how many questions have been answered correctly and how many questions are not answered correctly. Whose answers you want to use to, or whose representation you want to use to improve the representation of your model. So certainly this is not a one epoch case. In the first epoch you will learn as it is, and the second epoch is where you will try to start infusing your knowledge, because in the first epoch you will understand to what degree of questions a model is capable of answering and which of set of questions the model is not capable of answering. And that forms our new set of loss functions that we want to introduce, where the T is the total number of questions in the SCID, and the Q tilde are the questions that have been answered incorrectly by the model. So the difference of this would be that the learned representations are correct, and with the tilde, the questions, we introduce the responses for these questions into the learned representation so that the model can learn to generate good questions over the time. Now, the reason why we want to introduce response is very similar. You are aware of squad dataset, which is the benchmark of conversational systems. The squad dataset requires a context and a question to give an answers. If you if you put the response to the along with the context, you can get an answer. You can generate a question. So that's what essentially the idea here is. You want to concatenate with a series of representation. Your HL representation is completely questions, and if you concatenate to this a response, you will end up generating a series of responses, and your model will be trained to generate the series of questions, because now you are concatenating. The response becomes your context and HL becomes your series of questions, and the next series of questions that will be generated will be defined by that context that you have augmented into your model. So this set of structure forms the deep infusion structure, because you are dealing with this information at every layer. So there are various benefits of such detailed and such approaches. First of all, you're forcing the model to capture the context, because now, as of like without these information, the model is completely define its information based on the input data, which is kind of a partial representation of the world. You can help solve the uncertainty and risk association problem, because now you're dealing with a well-defined structure at every layer. But if you develop a better data set and the shallow infusion, that's where you control your uncertainty and risk. If you introduce this information, an interpretable ML model that is learning over this process knowledge, you have a less risky system. And another is a deep infusion, where you are regulating every representation with the process knowledge. Your model is interpretable, as I said, because now you are defining a. So when I'm doing a shallow semi-deep infusion, I told you about the interpretable ML model, which are interpretable by the definitions. In the deep infusion, you are matching it with the clinical questionnaire, and the questions that are being answered and not answered will tell you a ballpark region where the model is heading with its learning trajectories. User level explainability is achieved because now you are actually matching your outcomes to some clinically approved questionnaires, and the clinician knows which question have been answered by the model, which questions cannot be, which was not answered by the model, and they are the questions that the model will be asking next. And the most important thing that we are heading towards with this structure of knowledge infusion, specifically the process knowledge infusion, is a task transferability structure, where we say that we build a model in a way that if we just replace the forms of knowledge to the particular task, the model is able to adapt itself to those tasks in a pretty easy manner. So this is pretty much different than a transfer learning, because now we are letting the model be able to learn over the task and not simply over the data sets. So there are certain challenges that we will be uncertainty and risk, user level explanations, and self-explainability. In the reinforcement learning framework, and how it can be used to answer some of these challenging questions in a very so I would say not a high level, but it's more like a in a. So the remaining tutorial will be a primer for reinforcement learning, just talking about the knowledge infused reinforcement learning and various ways in which you can achieve user level in action. And we will conclude with the summary and the future work, which are the directions where we are heading with the.
Thanks.
Okay. Okay.
Okay. So just a brief introduction to reinforcement learning. Yeah, essentially it is at the core of it, just learn to make a good set of decisions towards achieving some reward. So the sequence optimization is more important than short-term strategies. How do you do that? So, like with humans learn, they interact with their environment, then they learn sort of an optimal sequence for each person's point of view. A reinforcement learning algorithm learns much the same way, by interacting with the world around it, gathering reinforcements or rewards, and then setting up the optimal sequence of actions. Yes, like I said, the reward is the same meaning as reinforcement. It's an objective measure to learn quantify the quality of the action of the interaction with the environment. For example, a reward could be if the reinforcement learning agent is learning to walk in the world. If they tumble or fall down, you could classify all that into -1 if they're walking normally, and if they're um, doing even more complex activities, then you could classify all that into +1. So there could be binary choices for rewards. You could have graded rewards. All of these are numbered, quantifying what the algorithm should learn. Yeah, the most important thing to note here is that initially the environment is completely unknown to a reinforcement learning agent. And so it is essentially a trial and error procedure, and often takes a long time in complex tests. So this is an example to show illustrate how the reinforcement learning algorithm works. Like, you give a dog a treat and then it learns pretty quickly. And if it doesn't do something right, then you don't give it a treat. Some may even use some form of pain therapy. But the thing to note here is this is just illustrative. A dog learns far more quickly than a reinforcement learning algorithm does. So the slowness still remains. Yeah, so we're going to do the same with machines, similar to what we do to a dog. That is the idea of reinforcement learning. Yeah, what is a scalar feedback signal? It's a single number. It's not a vector. There has been some work on it being other kinds of structures, the reward, but in the canonical formulation, it is a scalar signal, which indicates how the agent is doing at each time sequence. And the goal is to maximize total reward across all the time sequences, and theoretically, the time sequence is extended to infinity. Yeah, the framework was built under the assumption that any goal that you want to achieve can be described by maximization of some cumulative reward. These are existing reinforcement learning algorithms that can do some of these tasks. The chess, for example, it beats the world champion, so it's really good. Managing an investment portfolio is not there yet, but it is still in use. Controlling a power station, once again, it's very good at. And then making a humanoid robot walk, that is again not completely there yet. So what you'll see common among these is that controlling a power station have less toggles. Controlling a chess, even though the state space is large, it has at least limited controlled number of actions. Managing an investment portfolio or a human robot walk is more complex task. So reinforcement learning takes a bit longer. Those. Very simplified, this is the illustrative diagram for it. And the agent and interacts with the environment, gets an observation. So if you're already familiar with reinforcement learning, the observation is the full state of the environment, which is that there's nothing missing from your observation to describe the environment. Of course, realistically, this is always false. You only get partial information. So then you also get a reward based on the partial information that you see. And then the agent learns to train a function that maps the observation to actionable sequences. And in the rest of this talk, we're going to talk about how knowledge can help model these actionable sequences. You can skip to the next one. You can skip this. Let's go to the knowledge infused learning section. Yeah. Okay. So where does knowledge help? Most obviously, for specific problem of reinforcement learning. And the other issues that knowledge helps with, Manas already covered. I will reiterate, but for specifically reinforcement learning, it helps tremendously with the efficiency. Also, it helps user level explanation is also a great advantage. as we have found with our experiments and collaborators. The reinforcement learning in the extremely complex environments, it tremendously accelerates the convergence of the learned action. This is a summary definition of what knowledge infused learning is. It incorporates many kinds of knowledge into the policy function. The policy function is the map from state and observation and rewards to action. Okay, so this is a very simple illustration of how the architecture works. We'll see it expanded slowly with further applications. So there's data from the environment. There's the knowledge infused RL algorithm and some form of state representation. And then the knowledge comes in externally. The knowledge infused action is learned. And then because it has knowledge component in it, its explainability is also evaluated, and that may lead to proving some gaps in the knowledge, so the knowledge can be updated as well. Yeah, here is a paper that me, Manas, and others wrote about a year ago. This was at the height of the COVID pandemic. The simulator here is built on CDC data from in and around the New York region. And then logical features are constructed, which is the relational feature extractor. And knowledge graph features are also constructed, which is again part of the relational extractor, as well as flattened statistical representations are used for textual data. And knowledge about the ground truth is simulated and entered into the knowledge infused policy gradients algorithm. All that information is aggregated and fed to the actual policy gradient algorithm that is standard. And once the action is learned, the interpretability is assessed. And interpretability does not necessarily mean explainable. So then it goes to evaluation by the domain experts, and knowledge once again is updated if necessary. This is an example of what the learned policy looks like. Here it says that in a particular state of the world, a residential area is in the same state as a shop. A person is in the same state as their home. And then the home and residential area are also in the same region. So in this case, all these are very interconnected, the shop and residential area. So there is a possibility you might need to lock down this region as these are all universally quantified clauses. So there are many people like this. Go ahead. Okay. Now we'll move on to another application, the mental health chatbot to handle patients with depression and anxiety. First few slides, I will show an illustrative execution of the overall flow, and then we'll see slides from the demo of the actually implemented system. So the idea is that you use a user profile graph and clinical guidelines from the expert, construct the graph from the user provider notes, and type it by linking to UMLS. That is what happens in that blue box. And then the reinforcement learning algorithm has all the necessary information, and it learns to do based on user feedback as well, which is patient feedback. One of many actions, but we've shown here 5 of them. Appraisal means that it can praise them for following their therapeutic routine. Information gathering means that there's some gaps in the knowledge, solicit information from the user. Symptom check means that you do routine. It's similar to information gathering, but pertaining to symptoms for their particular case or medication that they may be taking. Health promotion safety is that if the reinforcement learning algorithm comes up in nothing, then a safety trigger is established to contact the care provider or another crisis resource. Reminding clarification is to just remind them of medication or other therapeutic measures they're going through. And there are several others. Yeah. For the end-to-end system, once the RL algorithm is established which task to do, the work is not finished. It has to actually operationally execute that task. So for example, if it is information gathering, there's a schematic information from the knowledge graph, as well as from statistical features from neural networks, not shown here, which can result in some algorithm that does dialogue generation and updates the knowledge graph, and the loop repeats until the policy function is stabilized. Yes, so we have talked about user level explainability quite a bit. Like Manu said, it is at the crux of it, a way for the end user to understand what the machine learning algorithm is doing. So let's see some examples of that. Yeah, we use several kinds of knowledge. So definitions from textbooks, knowledge graphs like SNOMED CT. So you can see here an example of how both can be combined to show the user a good visual of what is going on. So all the highlights are connected to concepts in the knowledge graph. The highlights are also matched with the definitions from the textbook, and a potential diagnosis is recognized. This in contrast to for a language model with state-of-the-art explanation strategy today, it just has the highlights. The second kind of knowledge is process knowledge, and that it is much more clear-cut how the explainability is achieved here. Not how, but what it looks like. So the sentence is highlighted. Exactly what sequence of questions does his answer in the flowchart is highlighted, and then the label is provided to the expert. Yeah, this is an example of what it actually looks like. So I've been there and got nothing, same as my life. This is a clear indication of what you see in 1, 2, and 3. The second sentence, I am not on a ledge or something, but I do have my gun in my lap, is once again an indication of 3, 4, and 6. So it can either be ideation or behavior or attempt based on the flowchart. And then we evaluated our approach with experts. The best performing large language model baseline got it right 47% of the times, and our approach got it right 70% of the time. So there's still room for improvement. 30% is still not acceptable, but the progress we're making is towards trying to explain how the models work slowly. And this is what the program actually outputs. It's the same thing as what you saw just now. That's just the format that it outputs in. I wanted to show a few examples of it. Okay, so now we'll move on to some examples of the system that I described before, the mental health system. from the actual implementation. So first, we construct a baseline. The baseline is GPT-2.
Should I turn on the demo?
Oh, it's not part of this. Yeah, turn on the demo.
Okay. How do I?
Is that presentation 6 file?
Oh yeah, this one.
Yeah, yeah.
Okay.
Okay. So how does initial assessment happen first? Similar to when a patient first enters the clinic. So first, again, we are going to see a baseline model, which is a large language model. So the bot asks, do you feel nervous? Click next, Manus. The patient responds with more than half the days. And the bot responds with, this example was already shown by Manus, but responses that are not considered appropriate, destructive, extreme, these words, no patient is comfortable talking about. And so it should not be asked directly. So once we infuse process knowledge into it from the PHQ-9, let's see what happens. The same conversation repeated. These questions are much safer to ask. They have in essence the same intent as the previous questions. They're just worded in appropriate manner. They're guided by question 8 in the PHQ-9, which shows irritability and restlessness. So one thing to note here also is that we are using large language models, but only constraining them in knowledge guided ways. So language models are not out of fashion. We are still using language models, but we're also constraining them so that we can control their functioning better. Yeah, this is suicidal behavior detection specifically. Here, GPT-2 really falters. The first response is okay, but the second and third responses are completely inappropriate. So then, once we infuse the process knowledge into it, it's better, as we'll see in a minute. Yeah. So this is much more useful to an expert because it tags exactly which concept was found. Question 1 pertains to wish to be dead. Question 2 pertains to non-specific active suicidal thoughts and so on. It also gives a follow-up action anyway, whether before even showing it to any user, if there is any extreme behavior found, then with an urgent notice, the care provider is alerted. Now we'll talk about some other action, medication reminder, and how it can figure out some potential causes for the troubles that the user is having. So from the provider notes, it is obtained that the user takes a particular drug called ziprasidone. Then once the question is asked, why is it asking about fluoxetine? That is given in previous information given to it directly by the domain expert. But now that it knows that and the user has confirmed it, it will add it to the user profile graph. Now, continuing the conversation, for fluoxetine, a lot of external knowledge is available, that it is an antidepressant, it has this class, it works on what kind of chemical, it is used for what disease, and how is it available when you have to shop for it. Using these kind of information, it continues the dialogue. And very importantly, what are its counteracting medications? So you see here that the bot is intelligent enough to ask if they've been provided with refills, because it sees that fluoxetine is available only by prescription. Now, when the user says the meds are not helping, when the bot registers this information, it also sees that fluoxetine counteracts something that the user is already taking, and constructs a potential hypothesis and alerts the care provider. It doesn't talk to the patient directly of this. It's not a medical expert, so it just continues the conversation. Continuing on with fluoxetine's external knowledge are its various side effects. The next line of conversation, because they said that it does not help me, is to investigate further. Yeah, so irregular heartbeat is matched closest to that. These matchings happen through similarity functions. And that is noted with high urgency to alert the provider that this is possibly what is happening with them. Self-appraisal checks, this is once new provider notes are present and the issue has been taken care of. There's new directives like exercise frequency. So that is now what the conversation will be about. Yeah, so that's the end of the demo. It praises the user for following their therapy routine.
Okay. So, moving forward with what Kaushik left us with, that with knowledge infused learning, you can actually control your series of questions or the conversations that the model is doing. And we have been talking a lot about mental health and other associated disorders. And what I wanted to tell you in this line of work, that what Kaushik was talking about, that in this setting of conversational systems, we are very much interested in how agent initiates the conversations as opposed to user initiating the conversation. So we wanted to see how does an agent would help in a different context or a different arena where the user is now seeking information. So in the Kaushik's use case, you saw that it was a clinical setting where the conversation is happening in a way that it is being used to inform a healthcare provider. And in another case where we want to see that how users are looking for helpful information to cope up with their mental health conditions online, and how an agent can help them in achieving the information that they desire the most. So I want to give a quick definition of conversational information seeking. It is a new paradigm within the conversational AI, and it really enjoys the concept of knowledge infused reinforcement learning, in specifically because there is a lot of knowledge that goes behind in a Google search. And we all know that Google search utilizes Google Knowledge Graph for enhancing your experiences in the search. And something similar is what you're going to be seeing in the context of mental health care. So conversational seeking, information seeking is an emerging area within the conversational AI, but essentially where we want to do an interesting application of CIS is that it's here the agent is the propeller of a conversation with a user. So rather than user being the driving force of a conversation, here we want the agent to be the driving force of the conversations after user has initiated his interaction with a query. So there are particular directions in which how users seek information, and it is not very similar as how your conversations are happening with an agent. Here, the information that the user is looking online have a particular structure. It's a particular questions, and it covers some series of details, and it also expand on some breadth of on a topic if the user is not able to find his required information online in a very quickly and easy in a fast manner. So that's kind of like a property of a human information seeking, which we can boil down into an implementation area within the paradigm of conversational AI as task oriented conversations. Like, for instance, seeking information for preparing a delicious cuisine. A user is seeking information about a health condition, and there are particular question styles in which users seek information. They are very contextually driven questions, they are lexically very sound, and they are syntactically diverse. The user by himself, his mind use them, he's used his experience to diversify his query. But most importantly, when a user searches information on the web, it actually looks for information in a very semantically related fashion, and the sequence of this question are in a logical order. If I don't find this, maybe I can find B, and then I can infer from B I can infer A. If I don't find A, I don't find B, let me ask C and infer B and A from there. So it's kind of there's a logical order associated with the information seeking things. And the most reason for this information is that with the particular order, the responses that the user is getting is a concatenated response of all the search results that the Google has provided to the search query. So the task here in the conversation, if we want to develop a conversational systems along these properties, then it needs to be task oriented. That means very much understanding of that what the user is looking for, what are the ways a user desire his information. There may be various context, different styles. And the third, when the user is finding this information, I should be able to, or the agent should be able to keep track of the entities and the actions, and then generate some, utilize the sequence of procedural questions that the user would be asking. I'm saying would because now the agent is driving the conversation. User was just initiated with one query, and now the agent is driving the conversation, and the task is now that how these questions that the agent is generating by itself, how the responses of those questions concatenated together would be the final response that you will be giving to the user. So that's what we term as response shaping. So this iSeek, which we built as a new conversational information seeking system, it utilizes some meta information strategies. When I say meta information, it is like supportive information that may or may not be a knowledge graph. So in this case, the meta information are a passive source. For instance, I can use DBpedia as a knowledge graph, but I can use Wikipedia passages as my meta information. So certainly knowledge graphs, DBpedia knowledge graph is rich enough, but maybe some information that has been newly incorporated into web pages or into the documents are essential compared to simply using the knowledge graph. So you want to do the best of both the cases. So the benefit that we are getting is now, if you utilize clarifying agent or a follow-up question agent, which have been already there in conversational AI, we do a way better structuring of the conversation. So if you look at the iSeek, how does it work is that If you ask it a question, it asks you back a series of questions. And these questions have already responses associated with it, because that's what used to construct these questions. The task of the user would be simply either provide these questions, responses to these questions, and the user will just map those responses to the responses that it has already aware of from some crowd thing. Or if the user what do you call if the user provides a response and the agent does not have those responses, then probably it would ask some follow-up questions very similar to what I was talking about in a process knowledge structure. So here, for simplicity, what we have right now in iSeek is the capability that it can ask you these follow-up questions. They are more information seeking, like getting more information from the user, and these questions already have responses associated with it. So now the user provides some responses to these questions, and the agent will simply map the user provided responses to the responses that it already have to find that what is the right suggestions that the agent should provide to the user. So now everything is in constraint based, and since all these questions are asked spontaneously, you are not doing a multi-turn conversation anymore. You are doing a single turn conversations with agents. So this reduces the turnaround time in getting the response. So we tried this in a general domain. The reason I am putting this this discussion in this tutorial is because we have been talking about mental health. So you might be asking, how does it work in any other domain? So here we picked the top searched queries on web right now, and they are from blockchain. And let's say the user asks a question, I need to learn about blockchain and its relationship to cryptocurrency and their importance. So if you look at a T5 model, which is a very large model for language generation, it generates some questions and asks some questions to the agent, to the user, and user reply back, and then it asks you another question and you reply back, and so on and so forth. But essentially what you're seeing over here is that the deep language model is prone to generate some irrelevant questions. For instance, do you want to know blockchain and currencies? We all know that blockchain is associated with cryptocurrencies and not currencies, and there is a difference between cryptocurrency and currency. So in that sense, this particular generation is irrelevant. And not only this, there are major cases. If you keep on doing these conversations, it will always be around the entities that is being present in the user query. So that means it's not able to expand to various other entities that are related to the entities in the user query. So so there's no redundancy in the outcome, and the diversity would not be there because it's kind of localized to the user query itself. On the other hand, iSeek, what it does is that when you give it a query, it constructs a small subgraph associated with that query. This subgraph is constructed using a knowledge graph. In this case, was a concept net. And essentially the task was, based on this small knowledge graph, I will retrieve a series of passages. When I say passages in this context is the Wikipedia, I will retrieve Wikipedia passages, and within the passages, I will find where these information in this knowledge small subgraph is been present. I will pick those set of paragraphs and I will train my model to generate questions from those passages. And once the questions are being generated, they are being asked to the user, do you want to know about these information? The user checks, these are the information that I would like to hear, and the agent gives you the accumulated response of this process. And the fascinating thing is that this subgraph you can construct in any domain. This task of generating the questions is not dependent on the domain. It is dependent on the task that you're interacting with. And in this case, the user wants to seek information from the agent. And it's really, really fast compared to a baseline, large language models. So let's just look at the workaround of how does this thing looks like in practice. So again, you have a query. Now I'm moving into a different domain of economy and employment statistics. And this is another domain of querying. And the user wants to know about GDP, inflation, and employment. So the first thing that we want to do is we do constituency parsing. And this constituency parsing is nothing but simply a structure of what you call so this constituency parsing is about the noun phrase extractions. And essentially what you're trying to do is that you are extracting a large series of noun phrases. And these noun phrases are nothing but nouns and some of the other nouns and nouns, or it can be nouns and verbs, and so on and so forth. So it's kind of a tree that this constituency parsing would yield. Now, when you have these series of, I'm already focusing on noun phrases, you can actually expand it using the verb phrases as well, but it's always better to start small so that you do not bring in noise into your graph. And you construct this particular kind of a graph, that is a concept net graph. Now, once you constructed this concept net graph by repetitive querying the graph based on this these keywords, I'm just trying to tell you that this graph can be as huge as is possible, because concept net gives you a lot of information, and you need to constrain those triples based on the information that you're providing in the constituency parsing. So, sorry, based on your identified noun phrases. Now, what you do is that you traverse this knowledge, this concept subgraph, starting from the leaf nodes up to the root nodes, and you are forming different set of triples. So now the triples would be: income tax is associated with income, income is associated with the cost of living, and cost of living is associated with inflation. And even unemployment, which is not present in the query, was also identified as one of the node, and you are saying that unemployment is also related to inflation. So you form various versions of your input query. Now your input query is not associated with only the query that the user has provided, but various variants of those queries. Now, once you have done this, you can retrieve passages by simply doing a string search of these triples onto your Wikipedia passages. But we found a better way, which is called dense passage retrieving. The way it does is that the triples that you're getting, you pass those triples. Now, when I say triples, it's subject, predicate, and object. And if you look at subject, predicate, and object, are the core of any sentences. So essentially, you can use a sentence BERT encoder to generate an encoded representation of a triple. And what you essentially do is that you use this information, this representation, to query passages, to retrieve passages from Wikipedia. And these passages, now when I say retrieve passages from Wikipedia, means the Wikipedia dump needs to be stored into a resource that can facilitate this kind of a numerical representation based retrieval, or dense passage retrieving. So what we did was we used the Facebook AI semantic search engine, which is very similar to Elasticsearch, and we retrieve the passages from the Elasticsearch, and you are computing the similarity between these passages and the representations of the query, and you found, let's say, top 10 or top 15 or top 20 passages. So that's your knowledge guided passage retrieving system. So what we did was, now you have a representation of your query, and now you have a representation of your passages, and you pass them through a generative adversarial framework. The reason I'm putting generative adversarial, I will get back to you, get back on this as well subsequently. But assuming that for now, for the sake of simplicity, that there is a generative adversarial reinforcement learning framework, and the reason we want to put reinforcement learning system is because here we want to utilize the capability that if a user wants to give a feedback, then or kind of an improvement or keywords, then the model should be able to adapt itself. So if you leave the concept of reinforcement learning separate, then these are the questions that the model is able to generate. And there are two categories of the questions. One is in the black and one is in the red. The red question, if you look at, are the questions that are not even present in the user query, but the model was able to generate thinking that these questions might be relevant to the user. Maybe the user was not able to provide more elaborative information on what he or she is seeking. So that's the benefit of having iSeek, and which is able to use some query subgraph in generating these questions. Now, how do we do this? So that's where I will talk about generative adversarial RL framework. So starting very basic, let's just take a T5 model, which is off the shelf, is capable of generating questions. And the same issue arises in the context of mental health, that the generated questions are completely devoid of context. They do not have any relationship with each other. They are just being questions that are being asked without having any order or any human related activity, human associated behavior. Like I would not say that these are the questions that a human would ask. So we say that, okay, let's stitch to this class generator a neural passage retriever. Now the reason we want to retrieve the passages, we want to augment this passage retriever to this generator, is because the generator by itself is completely driven by some kind of a pre-training that is being run on some open domain corpuses. Neural passage retriever, on the other hand, will actually retrieve passages that are very much specific to the context of the user query. And you now fine tune your generator again on these passages. Now, when I say fine tune, assuming that I'm fine tuning with the standard behavior that your passage is there and you're concatenating your passage to this user query that the user has provided, and you fine tune your generator again. The reward would be the generated question being matched to a ground truth questions, and you back propagate and you improve your retrieval mechanism. Done that, if that done correctly, you're able to capture the context, because now your passages are very much related to the user query. But the semantic relationships and logical ordering behavior in these questions are not there. Now, if you look at the previous slide that I was talking about, the question that my IC was generating was in order. The reason the order is because the human information seeking behavior is in order. So we want the questions to have some semantic relationships, and we want them to be in order. And this, on the other hand, is also prone to generating some unsafe questions that probably might hurt someone's sentiment. So, or might have some negative connotations. So we wanted to control these A, B, so we achieve A with this neural passage retriever, but we are still looking for B, C, and probably controlling the safety issues as well. So that becomes the first variant of iSeek. That let's just control the first thing, which is semantic relationships. And we all know the knowledge graph, if you are like a concept net, they do have some kind of a relationships associated with it. Now, every triple in a knowledge graph has some kind of relationships. And that means if I say, if I just take one tree, or say, I say just one, one tree, I would say, then the tree entire is nothing but an order. Like it's just semantic relationships between all those nodes. So that means if I retrieve passages along these nodes, I would definitely retrieve redundant passages, because definitely the leaf node will contain all the information up to the root node, and the root node passages would not have any information in the leaf nodes. So we will be generating a humongous size of passages, but we will be keeping only those passages that has all the information being mentioned in all the different ways in which the query was expanded, right? So your neural passage retriever now is controlled, the order is now controlled by a knowledge graph. Now you have an ordered set of passages, you fine tune your generator again, and now the reward remains the same, and now you have a generated question which are in order of those passages. And if you look at them, these questions are in order, I would not say order, but they would rather be in semantic relationships. For instance, do you know what causes depression? Then you describe the depression, and then do you think you feel hopeless and depressed? And now it comes to the cause. What is the cause of sadness? However, as we can understand, cause always comes with the first thing. So the first question was already about, do you know what causes depression? Why does the model again ask the cause of the sadness at the last point? So this is where we say that logical ordering is important, because such cause type of questions needs to be together, describing questions to be together, and maybe if the treatment and medications are provided, they need to be in sequence with each other. So that's where we say that with knowledge graph, you're able to do semantic relationships. You can bring relatedness in this. Context is already there with the neural passage retriever, but the logical ordering is not still there. As I said in the very beginning of the tutorial today, that logical ordering is something that is not there in knowledge graph. A knowledge graph is not a logical order resource. So you need to have a resource separately that can actually introduce logical ordering. And that's where we latch on to a concept called natural language inference. The reason is the natural language inference principle says that if the two questions are in order of each other, then the second question entails the first question. If the two questions do not provide any new information, they are same, then they are neutral relationships. But if the second question contradicts the first question, then definitely they have some contradictory relationships. So in a very intuitive sense, what do we want to minimize? We want to minimize that the neutral and the contradictory relationships questions should not be generated, and the questions which are in entailment of with each other should be generated. That means that it introduces the order, and that becomes an evaluator network. So the evaluator network that you see over here is nothing but a trained network on a data set that introduce this kind of an entailment behavior. And for that we use the Stanford Natural Language Inference dataset. So like you can actually use some domain specific data sets as well, like MedNLI for medical natural language inference. But the mental health conditions or mental health care questions are not as clinical as it seems. They do relate very much to an open domain questions that people ask on the web. So that's why we took the Stanford language inference dataset, because that's being constructed on the web, from the web data. Now in this, if you can see, the questions are now well in order. So now you feel, do you think you feel down most of the time? Then you feel depressed. How long have you struggled? So these are the questions that you talk about the time that you are actually having the depression. And then you find the question, what is the cause that you are thinking as about the depression? So you kind of define some kind of a preliminary background in the first three questions, and then the fourth question is now about the cause, and subsequent questions can be about the symptoms and treatments and so on and so forth. So you have a whole series of an order in the question generation processes. So this is the task of the evaluator framework. So with this, I can actually share. So there is a lot of examples that are there about of this framework. If you want to look at those examples, I have provided those examples on my on the GitHub as well, on which is like github.com, like my minus Gaur, and then /AAI 2022, where we have given a lot of examples from various domains talking about policy, politics, news, and even travel planning, which require some series of question generations. So with this, I want to lay down what are future and directions, and where we are with this tutorial, what we just delivered today. So we showed you a fascinating way of incorporating knowledge into your models, not only knowledge graph, but various other forms of knowledge. We introduced today that knowledge graph is a non-sequential form of knowledge, and we find there are use cases in the current domain where we want sequential knowledge to be incorporated into the AI framework. This knowledge acts as a system 2 and interacts with system 1 to be able to make decisions that are user level explainable. And more together, the symbolic reasoning framework introduces the interpretable component of the statistical AI black box. And we told you about the three forms of shallow infusion, three forms of infusion, which is shallow, semi-deep, and deep infusion. And where we are working right now is more towards the deep infusion structures. So in this arena of knowledge infusion, certainly the data sets that we already have are which are benchmarking the natural language processing community algorithms, are the general language understanding evaluations. But what we want is a knowledge intensive language understanding. The reason is because these data sets, what we call glue data sets, do not challenge AI for explainability and interpretability, whereas KILU does. And parallel to KILU, there are another set of data sets called knowledge intensive language tasks, which are KILT, and they are also specific, are also used to challenge AI for explainability and interpretability. KILU, on the other hand, are very much specific to the social good aspects, more specific to mental health, crisis response, and more challenging problem like radicalizations and so on and so forth. Whereas KILT are still the open-ended, open domain question answering systems, or more open domain conversational systems. So what how KILU differs from GLUE is that KILU was constructed keeping in mind the structure of the problems that are being illustrated in GLUE tasks, But here we want to motivate the development of those data sets that necessitates the requirement of knowledge. And essentially, if we want to do knowledge infusion, you cannot simply use F1 score or accuracy metrics alone, but rather you need some more richer metrics to evaluate your outcomes. So with KLU, we introduce some rich evaluation metrics, and these evaluation metrics are being used extensively by broader communities across. And these evaluation metrics are essentially being constructed from learned language models, the trained language models on variety of corpuses. Our direction that we am heading right now, along with my team at AISC and Kaushik being a part of it, is a multimodal conversational systems for autism assessments using ADOS. So as I said, we very sticked in this tutorial to the process knowledge, and ADOS is a process knowledge for assessing the autisms in children. So we want to utilize how the ADOS process knowledge along with various diverse forms of knowledge can be used in assessing the in assessment of autism for children at an early stage before it can scale up to some unforeseeable situations where treatment is either costly or is not possible. So in this process of autism, I want to give you a very high level view of what the directions where we are heading with this IDOS. We have observational data, which will contribute to our NLP feature extraction pipelines. But we also do have assessment tools data, which is question answering, questionnaires, lab reports, and so on and so forth, which forms as other features of the data, including the process knowledge. And we wanted to train the model in this multimodal fashion that will yield a vector that will tell me whether to what degree of assessment, what degree of severity of autism does a child possess. And once we have this trained system, we want to use its parametric knowledge, its learned knowledge, into a personalized interactive conversational system where the agent is interacting with the children, with the child, and giving up a score, and that score is given to the care provider to define a proper intervention plan. So that's the whole idea of this personalized knowledge graph structure for autism assessments. And user level explainability is at the core of this structure of this direction, where we want to use that if we have a strong lab reports or information that we are using in the model is capable of not only delivering that vector that I was talking just now about assessment of the autism, but it also highlights some of the piece of information from the lab reports that would tell me why this particular vector was generated. And essentially what you do is that you use that feature vector and construct this graph of this kind on the left using a search and retrieve method, which is at the core of knowledge graph and semantic web community. And you construct this graph for the autism. And you see that because of this graph, this particular label was being provided. So you are gaining some set of now user level explainable system and trust in the system. So these are like the immediate directions along the autism assessment that where we are heading in the research. And these are the references of the papers that we have published in the idea along the idea of process knowledge infusion in general, and knowledge infused reinforcement learning, both in a normal textual in a classification task as well as in the generative task as well. So these are the two tasks that we have focused in improving the current state of the art AI strategies. With this, I would thank all my team members at AIC who helped us put together this tutorial and motivated me and Kaushik to actually deliver the directions as well as strategies, methods, and policies that we are developing in improving the AI using the knowledge graph and using the knowledge structures. That's a term that I would be heading into, because a knowledge graph, as I said, are supportive, but there are certain limitations associated with the knowledge graph. So that's what we motivated in the tutorial, our direction towards process knowledge. And I do acknowledge Vedant, who has helped us in constructing the demo for the virtual health assistant for the mental health. And this research has been generously supported by the National Science Foundation EAGLE grant. And now I am open the arena for questions. Any questions from the audience we would like to answer? Any lengthy questions, even if you have any lengthy questions, do feel to send me an email. If you have really quick questions, then we are happy to answer that.
Yeah, the participants could unmute. Hello. Hello. Am I audible?
Yes, you're audible.
Okay. Thank you for this wonderful tutorial. Basically, I have a lot of questions to ask. Yeah, the first
Okay.
thing is the data sets that you have told regarding the Columbia suicide severity rates and the PHQ-9. So
Yeah.
the answers were means the labeling was just yes or no, right? But it is
Yeah.
not always necessary that the user will always respond in the kind of binary answer, right?
Yeah.
So
Yeah.
what if they give any some kind of a neutral answer or like the answer?
Then we will consider them as no.
Oh, okay.
Because
Uh,
the reason is that if there is a probabilistic situation, it's very hard to do your thresholding.
uh, okay, and
And
then
yeah.
when you are saying means the agent is going to build the conversation. So what level of utterances you are considering for this? Means just the previous questions or the previous questions to build the knowledge? Means what exactly is happening with the user?
So any historical questions that the user has involved in the past, all the questions are being used to train the model.
And okay, and what if the user is interacting for the first time? Means
Yes. So if the user is interacting for the first time, so that's a cold start situation, very similar to the recommendation system. So what we do is that essentially till the we have sufficient interaction from the user, we use some crowdsource information. So we say that if we have historical conversational data on which the model has been fine tuned, initially the model will be seems to be less engaging, but as user starts providing more and more information, the historical database that we have for the conversations kind of starts to narrow down into a small bucket that will tell me what context the user is heading to, and that forms a seed, and over the seed the new conversation starts to build up.
one more thing I would like to ask that you said that the agent is building the questions using the paragraphs, right?
Yeah.
So means here for the dialogue managing system or for example the sentence realization. So how you are maintaining these emotions, empathy, sensitivity, sentiments? Means it
Perfect.
should not look like that a computer is talking. Like users should have a feel of a human is talking to them. Then only they'll be able to open themselves, right?
Exactly. So right now that's one of the direction that I would like to pursue, the emotion aware natural language generation, right? And that's something that I was not focusing as of now, but I was focusing in this process was that how I can generate how I can make a conversational system that can mimic some part of the human behavior, which is focusing on the context, then focusing on the what do you call the semantic relationships between the questions that are being generated, and there should be a logical order. Empathy and emotion sensitive generations can be achieved because there's a lot of lexicons, and you can even there are some data sets that on which you can fine tune your model to make it more empathetic. But empathy not only comes with fine tuning, but it will also requires some set of constraints being used. So you want to check which to what degree of sentiments or emotions are associated with the generated questions, and if they do not match to your degree of emotions and sentence acceptability, you would kind of remove that those questions. So Pooja, to your question, you can use iSeek as a process to train your emotion aware natural language generation, but iSeek as of now was only focusing for 3 functionalities.
Okay. So as you have talked about Isaac, actually, I have a question too for that also. I saw that the image means how the Isaac is working. So what you showed that means when a user is asking something, the agent is actually giving a list of the questions, right?
Yeah.
So means if you will talk about a common person or a common user, so they will exactly get. Don't you think frustrated by seeing all this list of questions? What means how can you then what should I say? How can you evaluate that before to which question the user is giving the answer? Right? Means it is
Yes.
obvious that they will get irritated if you just give the length of the means because he is already not in that mental state. Uh, that is why he is doing the conversation. And if you just give him fire him such a list of questions, he will again get provoked for. This is what the question that I want to ask regarding
Yeah,
Isaac.
yeah, definitely, definitely. So that's what that's the problem here is that so there are different forms of query puja over here. So the questions, so what told you that these questions are meant to be asked because the user hasn't provided us sufficient context, right? So I cannot blindly give a response to the user without following it through a certain sequence of questions. So even if you take any deep language model right now, if you give it a short query like this, it will yield a kind of a very nonsensical response because the response that is being generated was completely based on the co-occurrence metrics computation, right? Here the task is that if this search the query size is very small, probably generating the response through a careful generated questions would be important. Now that being said, if a model is generating these questions, as I said in the tutorial, that these questions are being generated based on some paragraph that have been retrieved by the model. If those paragraphs, if the user does not provide the response to these questions, we'll still provide. So the reason we want to show these questions to the user is that we want to have an interactive or engagement with the user. I agree with you that the user might not be available to answer these questions, but essentially, rather than giving some response that is not useful at all, it's better that the user can provide us a little more information about what he's suffering through, so that we can provide them a much better response. Now, if these answers to these questions are already given by the user at the very beginning, we won't be asking these questions. Rather than we'll straight away go for the response. So that's what I'm saying. We are checking whether these questions are being marked yes and no. And if they are marked these questions, then probably they would not be asked. And some of the questions where I do not know, because I need to match the response. I need to match my response with a particular guideline. Else I might end up giving a response that might not be helpful to the user at all. So there is certain level of I would say negative point to this question generation, but they have to be done in order to control safety and be able to do not yield any response that might have a negative impact on the user.
Okay, thank you so much. Actually, these were only the questions that I wanted to ask you. Thank you.
Okay.
If there are any more questions from the participants, you could please go ahead. Okay, Manas, there is one question from my side. If you go to 69 slide number,
Okay.
As you just mentioned in this slide that yes, there are two systems. In system 2, we are infusing the knowledge. I could see there is an actor as well.
Yeah.
Because the question end user is asking, he is bombarded with more questions instead of giving a straight answer to him.
Yeah.
That is symbolic reasoning. So means to what level does it make a real sense?
So that's what I'm saying. So what I showed you today, the questions that are being generated are in the context of mental health, but these questions are not the questions that are being generated in a general purpose sense. So if someone is giving me a query about a travel plan, I would not ask him back the questions because I don't want him to see the questions, right? Because even if my response is little bit not helpful, it won't have any impact on the user. But
Yes.
if I'm talking about a mental health care, I need to guide my question generation to a particular process, and that's why I need to generate a question and being reflective to the user on whether these questions are worthy of a cohesive response to him. And if he says that I want yes yes, if he says yes yes yes, and whatever response, will still give a cohesive response to those questions, because those questions are now governed by a particular questionnaire. So that's why. So there are two application area of iSeek. One is the general domain, where we do not want to show the we do not show the questions to the user, we just give the response. And the mental health care, where we have to share the questions, so that the we are controlling the behavior, we are not going too bad in the conversations.
Yes, I understand, and I suppose that after the model is well trained, then
Yeah.
the number of questions will decrease thereby. Is it?
Yes.
Okay,
Over the
that
time,
makes sense.
definitely. Over the time, definitely.
Yeah, that makes sense. Yeah, we could get it.
Yeah. So I would like, if someone wants to try something new, then there is a very active model right now. And if someone wants to interact with me on an email, do send me an email about their questions. But I would like you to try Jurassic X. That's a new language model. And if you pass that query, a very simple query like what is the difference, or you can say that a simple query like negativity and jealousy, as the like these are the, like in a mental health context, these are very common words, negativity and jealousy. The model tries to give you a definition of jealousy, whereas if you look iSeek would generate some series of questions, and then an accumulated response of those questions is what is being delivered. And this is not just one statement answer that the user will get, but rather a good series of questions and answer pairs that the user will be getting, that would actually be helpful to him, rather than just one line definition which us persons can simply look at on the web and get an answer. So I would like you to guys to try Jurassic accent. I can tell me with various queries, and I can definitely give you the response from the iSeek as well, which still it is in functional with Samsung Research America, and will soon be a part of the Bixby program.
Okay, well done. I hope if the participants do not really have to say something right now, you could write to Manas and Kaushik on their email, and their GitHub accounts are already available. As he mentioned, there are lot of examples there for the various scenarios. And I hope over for today.
Okay.
Yeah, thank you, Manas. Thank you, Kaushik. Thanks for this wonderful tutorial from the AI Institute of University of South Carolina. Thank you
Thank you.
very much.